Uh, so let me start. I'm Yuko Okamoto, and I'd like to introduce Professor Michael Klein. He was born in London, UK, and he went to University of Bristol and got the bachelor's degree and the PhD degree. Then he went to Italy for a postdoc. Then came back to University of Bristol as another postdoc. Then in 1968, he became researcher at the National Research Council of Canada and spent there for almost 20 years. And after that, he became a chaired professor of physical science at the University of Pennsylvania, and another 20-some years there. Then after that, he moved to a present position of Laura Carnell Professor of Science and Director of the Institute for Computational Molecular Science and Dean of College of Science and Technology, Temple University. He won various awards, and one, just to mention a few, he won Rahman Prize, National Rahman Prize of APS, Division of Computational Physics, and he's a member of National Academy of Sciences. And if you look into the Google Scholar profile, you see many papers by him, and most cited paper is 38,627 times. This is about the water model of type 3P, etc. There are about 6 papers over 1,000 citations, etc. So he's the leader of computational molecular science. Okay. Thank you.
Do I get extra time?
Yes. Yes.
Okay. Good morning, everybody. Let's see if it connects again. Nope. Okay, so good morning, everybody. A pleasure to be in Japan and tell you a little bit about the history of modeling water. My current inspiration is actually my new partner, Dr. Anna Christine Huber, and her cat, which is called Higgs boson. And it's a very well-named cat because of its behavior. It seems to be able to tunnel in and out of places you'd rather it didn't. Anyway, I want to draw your attention to the fact that there's a significant anniversary this year. 1953 paper on modeling simple liquid using the second computer that was built of the modern style, called the MANIAC computer. The first such computer was built at the University of Pennsylvania, and it was called ENIAC and was delivered to the US Army Research Base in Aberdeen, Maryland. And Nick Metropolis and others from Los Alamos got to play with that a little bit and then ordered a machine for themselves, but it took many years before it was delivered. In fact, the MANIAC computer was delivered in 1952, long after the Second World War. The people that built that computer went off to create their own company, which generated the UNIVAC machines, and which I'll say a tiny bit more about later. This paper's significant because it signals really the birth of computational science, along with other work that went on at the same time in the Los Alamos lab. In this particular case, the use of a Monte Carlo method to do the sampling of the phase space of the liquid was very novel. Another unusual thing about this paper is, for the time, is that among the 5 authors, there were 2 females, and they were authors of the paper. It was the custom at the time to thank the females that did a lot of the work in the acknowledgement and not actually include them as authors. The case in point is the famous Fermi-Pastor-Ulam work that was carried out at the same time on the same computer in Los Alamos and appears in a Los Alamos report a couple of years after the work was actually done. And I've put at the bottom of this slide the acknowledgement from the main authors for Mary Singu, who actually did the calculations on the machine. This situation of putting the females in the acknowledgement was, as I said, unusual that this paper cited them. But there's a very good reason for that. When I grew up and started to do Monte Carlo calculations, we in the field referred to this method as the metropolis method. But what's really emerged over the last few years is that Metropolis's name was first because he was the guy that owned the computer, owned in the sense commissioned it, looked after it. And it wasn't clear that he actually participated directly. Whereas very recently, reading an obituary of Ariana Rosenbluth, it seems clear that she played a significant part in developing the algorithm. I mean, as we all know, an algorithm isn't usually designed by a committee. Somebody has a spark of an idea. Maybe the others discuss it, or like in mathematics, somebody else has to check the proof. But it isn't usually a committee that invents something. So I said this was unusual. There have been other claims to inventing this important sampling method. In particular, Bernie Alder insisted that he did it first. And in fact, I went back to check this original paper in 1953, and Bernie Alder is in fact cited in a footnote for having shared similar ideas with the people there. Although I overlapped often with Bernie and spoke to him often, back in 1985 he was challenged to explain how he did these calculations, and to those of us that were present, it wasn't very convincing. But in any case, he has his own fame to claim. He invented the molecular dynamics method, as we know. And here again, the work was done, the computations were done by Mary Ann Mancy, married name Carlson. And she's still alive, as far as I know. In fact, I point you to the CCAM, the European Center for Atomic Molecular Calculations website, which has 2 beautiful talks reviewing this history, one by Michel Maréchal that deals with the birth of the Monte Carlo and molecular dynamics method, and the second is actually an interview by Don Frenkel of Mary Ann, and it's really fascinating listing. This was from a few years ago. These original papers of Bernie are much cited. Anyway, what about water? I went to university in 1958, and in my 3rd and final year on the way to an undergraduate degree, we had to do what we call in the US a capstone project, or a very minor thesis, just in the rudiments of research. And I went to the head of department who assigned supervisors for these projects, physical chemist called Douglas Everett, and I told him I would like to do theory for my project, to which he replied, "Klein, chemists wear white lab coats." So the notion of doing theory back then in chemistry departments was pretty rare. I must have been persuasive because he assigned me a project on water and ionic solutions. He suggested I read this paper. This paper signifies the birth of chemical physics. It was published in volume 1 of the journal Chemical Physics, 1933. And the authors there, J.D. Bernal, the student, and Ralph Fowler, who was the professor of theoretical physics at Cambridge. Ralph Fowler was Rutherford's son-in-law. And in fact, I learned some of my physics from his son, Peter Fowler. Anyway, these guys set up to model water by a method which continued pretty much until 20 years ago and is still prevalent in the biophysical community. The idea is you try to encapsulate the electrostatics of the problem in terms of a model that's informed by the electronic structure. And in the lower right corner there, I've indicated straight from the paper that they already understood in 1933 there were van der Waals interactions that go over 1 over r to the 6th. They also understood that there was a short range repulsion, and here they cite Lennard-Jones, use the number 12, and the rest is the electrostatics. Of course, they didn't have a regular computer back then, it was just a hand calculator, and so any calculations they did were based on pretty rudimentary methods. Nevertheless, these people were not shy about claiming success of explaining everything known about water. Anybody interested should go back and look at the paper. The second paper I was assigned was to read the work of John Popel and an introductory paper by Lennard-Jones and Popel that was published in 1950. This was the year 1960 I'm talking about. So these were not as old as these papers. Very insightful paper, and again, not famous for being a modest man. I've underlined in red, it is shown that using a bending force constant consistent with the electrostatics of a simple model leads to a satisfactory explanation of the structure of the liquid, the discontinuity in melting, and also the dielectric constant. This is a bold claim, just on the basis of more or less hand calculations. So what could I do for my little project? I scratched around in the literature looking for a model that I might be able to do hand calculations with an electronic calculator, and used this model that came out a little bit after Popel from Bill Schneider to calculate ionic solvation energies. But I actually found this pretty boring. So after my undergraduate degree, I tried to switch to physics, to do elementary particle physics with Cecil Powell and Peter Fowler, Rutherford's grandson. They told me to go away and get a scholarship and come back, and then I could enroll as a graduate student. Well, on the basis of my undergraduate degree, I applied for and got a scholarship, but when I tried to register to do a PhD, the bureaucrats in London refused me because I was a chemist, not a physicist. And so I had to go back to the chemistry department and do chemistry. So that's the world. Maybe it's changed these days, I don't know. But in any case, they managed to assign me somebody who was a mathematical physicist, had trained in statistical mechanics under Cyril Dom, and the same supervisor as Michael Fisher and others. So I had a good instruction to begin. Unfortunately, my advisor died just a few weeks ago. He was almost 97 years old. So he assigned me a problem. The details don't really matter, but he gave me 2 papers to read, the original paper by Debye, 1912, and a review article by 2 German physicists, Leibfried and Ludwig. And then he set off for a year's sabbatical on another continent. This was actually marvelous for a graduate student. We had no internet. The latency of communicating with my advisor was 2 months, and I managed to do my first paper. My first paper came out in Physical Review, 1962. I was enchanted by many-body theory and physics, and I went to a conference in Copenhagen at which I was exposed to molecular dynamics for the first time. George Vineyard, who ended up as the head of Brookhaven National Lab, showed a movie of channeling of ions in crystals, which was done by integrating Newton's equations of motion by exactly the same methods that we use today, really. The algorithms was very similar. So that was very impressive from my point of view. The other things that I got from that was I learned about neutron scattering. And the marvelous thing at that time is that I got to interact with Max Born, Peter Debye, and then in the summer school I went to at the Chalk River Nuclear Lab on many-body theory. I had lectures and interacted with Walter Cohn and David Thowles. The legacy of these two meetings on me was the appreciation of structures of liquids and the time dependence, the space-time correlations, and that introduced me to an important paper by Van Hove, who did many other things than this, but for me was very influential, how you generalize the structure to time dependence and how the Fourier transform of the real space gives you what you would measure in the neutron scattering experiment. The Chalk River Summer School was fabulous. Walter Cohn lectured on Hohenberg-Kohn theory. This paper has 63,000 citations and was influential for me. I sat next to, in many of the lectures, Lou Sham, who was similar generation as me, and in my particular interests were more focused on Alexei Marodudin's work than the Hohenberg-Kohn, but nevertheless I was there when this theory was exposed for the first time. Lou Sham went off to do a postdoc with Walter Cohn, and that famous Cohn-Sham method for solving density functional theory has 71,000 citations. So these were significant works. Later that year, a paper by Anisur Rahman, which did the structure of liquid argon, very simple model, and that was a very influential paper. But it's more than a decade since the Monte Carlo version of this was done. One often wonders why did it take a decade to just solve the equations of motion. Anish was a fabulous character, unfortunately died too young. He came from a Muslim family in Hyderabad in India. Must have been a wealthy family because he was sent off to do his undergraduate studies at Cambridge. And his daughter shared with me this photograph there from 1949. He hitchhiked back to India after the semester was over. Can you imagine? He hitchhiked from Cambridge, England to India. I mean, this is amazing that he did that. Fabulous man. I got to interact with him many years on after that. Anyway, that digression about computer simulation brings me back to water. And the first simulation of water was carried out by an Australian, John Barker, who, as it happened, I was corresponding with in some of the work that I was doing as a graduate student, and met him on a visit to England in the early 1960s. And it turned out in the fall of 1968, I moved to Canada, and John Barker arrived in Canada at the same time at the University of Waterloo and shared with me that he was doing the modeling studies of water. This work is largely ignored, unfortunately, but nevertheless, I think claims priority of being the first to do this. John only survived one winter in Canada. It was too cold, and he moved to California. He was from Australia, and he moved to California at the IBM Research Lab and immediately invited me to visit. I spent the winter I escaped the Canadian winter of 1970, the January, February, March. I worked at IBM, and I also interacted with the people at Livermore. And access to a large IBM computer and collaborating with people at Lawrence Livermore meant that I had access to a big machine and did my first Monte Carlo calculations. I think that's an important statement. There were plenty of people that could have done this, but they never had access to the computer. And the only way I could get access was by collaborating with people that had such a computer or had access to such a computer. Later that year, 1971, Anisur Rahman and Frank Stillinger published their seminal work on simulation of water. Not cited so much these days, but again, claims priority. Things changed in the 1970s, though. These American computers proliferated around the world, and that meant many universities and university professors could get access. In my case, I worked with the people at the University of Paris. I was hosted in the high energy physics lab, the theoretical physics, high energy physics, where I collaborated with Lou Verlet at the top, not explicitly with him, but the members of his group, Dominique Levesque, who's beside Lou Verlet in the upper right, Jean-Jacques Weiss, and particularly Jean-Pierre Hansen was the person I mainly collaborated with. At the same time, at the same university in a different building, there was a big IBM machine, and there was the European Center of Atomic Molecular Calculations was created in 1969 by Carl Moser, as much famous for that as his dogs that he had. And I've got 2 pictures of him. So I visited both of those places, working with people in both of those labs. There was at that time, computers were mostly being used to test theory. The notion that they could be used to go directly to experiment emerged only as the computers got bigger and systems could be studied at higher degrees of accuracy. And my interaction with Jean-Pierre is more than 50 years old and still good friends. Did some wonderful work with him in the 1970s. Because the UNIVAC machine was in this high energy physics lab that Lou Verlet managed to get, and the other works we did involved the big IBM machine. Some of our works on dynamical structure factor came out in the 1970s. During the 1970s was the birth of the biophysics approach. There was a workshop at CCAM, and the fact that CCAM had a computer served as a nucleation point for people that wanted to do some test projects before they might go home and do other things. I point here to a seminal report from CCAM, from a workshop that was held in the summer of 1976, where a dipeptide was modeled in water. And the report is written by Peter Roski and Anisur Rahman. And that was the first I knew of these kind of simulations. There may be other people here that have deeper insight. I quote in this slide from Peter Roski's own words. He said that Martin Karplus had been in touch with Anisur Rahman, and Andy McCammon and Peter went to this workshop in '76. By the way, I was on sabbatical at the same time in Paris, using the same computer to do these dynamical structure factor calculations I just highlighted. And they were there for this workshop, and I put it there. So the interesting thing is the CCAM report is Roski and Rahman, but the published paper is Roski and Karplus. Somehow Anis's name disappeared. It would be interesting to know from the people involved what happened there and why Anis's name disappeared. Anyway, these characters, Martin got his Nobel Prize and shared it with these 2 Israelis. It was fascinating to me how these 3 were picked by the Nobel Committee, and it turns out that corresponding with Michael Levitt, it seems that although the origins of the beginnings of the molecular dynamics code CHARM, which is used widely in the biophysics community, were from the Karplus's group, gained from Ariel Warshel and Michael Levitt, but in fact developed their own code. Another important point for those of us that are interested in flexible molecules was an algorithmic development in the 1970s, which enabled us to handle a method of autonomic constraints. The flexibility of the molecules got us away from worrying explicitly about torsions and so on. So that was a very important development from Giovanni Ciccotti, Jean-Paul Ricard, and Herman Berenson. That brings me up to the 1980s. 1980s was a year in my fields that algorithms were developed and new approaches. As the computers proliferated and became more powerful, people got interested in using Feynman path integrals, and in particular, modeling phase transformations on a computer. I'm highlighting a paper by Hans Christian Andersen, professor at Stanford. Hans Andersen was interested in trying to make a glass on a computer by quenching a liquid. And if you did this in a normal microcanonical ensemble, you have a problem because the density of the system changes. Freezing water, it expands, but freezing normal liquids, it shrinks. And Hans Andersen introduced the notion of coupling the simulation box as a dynamical variable, the so-called extended Lagrangian, so that you could, as you cooled the system, the box could also shrink self-consistently with the forces that were operating. Beautiful paper, very influential. That paper was quickly extended by Michele Paranello and Anisur Rahman to handle not just an isotropic dilation of the system, but a change in shape. So very often the crystals, when they go through phase transformation, might go from being cubic to monoclinic or whatever. And so the box doesn't just change isotropically, it has to be able to shear. At the Gordon Conference on Liquids in 1980, Anisur Rahman came running up to me, waving a manuscript that he just submitted to Physical Review Letters, and said, "Mike, you should do this for molecules." Actually, if it had been easy to do for molecules, I'm sure he would have done it. But anyway, I do acknowledge the fact that Anis pointed me in this direction. The seminal paper from Paranello and Rahman has 16,000 citations introducing this powerful method. 1982, I came to Japan. I was invited by Joshin Yamamoto to visit the chemistry department in Kyoto, and it was a fantastic visit for me, truly inspirational. I got introduced to Japanese culture. Coming from the UK, and I used to vacation in the southwest of England, very across the road, literally, I stayed from the Bernard Leach pottery, so I was well familiar with the Japanese pottery, and this gave me an opportunity to come to Japan, explore, and in fact to buy some pieces. It was really memorable for me. These are some of the fabulous works that I acquired at that time. When I got back after the visit, we worked very hard on these, extending the Anderson-Paranello-Rahman to molecular crystals, and our first paper came out in Physical Review 1983. Shuichi Noze joined my group after my visit to Japan. Phenomenal to have such an incredible person in the lab. We modeled all kinds of molecular systems, and the computer graphics was very primitive in those times, and that's the best we could do in the early 80s. Towards the end of the 1980s, very powerful graphics computers came out, and these things became much more easy to make movies and visualize. Shuichi worked on many things in my group. I think in the couple of years at the end, he published more than a dozen highly cited papers. But most importantly, the work we did with Shuichi Noze enabled us to collaborate with Bill Jorgensen and develop these water models that were tested both by Monte Carlo, constant pressure Monte Carlo, and constant pressure molecular dynamics, enabled the optimization. In effect, what we had done, 50 years after the Bernal-Fowler paper I was given as an undergraduate to read, we'd actually done the problem properly. Shuichi Noze, in the fall of 1983, came into my office with a manuscript which was, to me, earth-shattering. He'd come up with a method to do a simulation in the canonical ensemble, and I told him he better publish this on his own. I had nothing to do with creating this, and he published his first paper. It got through reasonably quickly, and then he did a second paper. The second paper, more highly cited, 17,000 citations. So those two papers on this new method he introduced together have 27,000 citations. So the fact that I was in Kyoto for 6 months in the Yamamoto group turned out to be phenomenal for me, and I got to interact with Shuichi. There's a photograph of him here in my house in Ottawa, Canada at the time. And these paintings were gifts to me from Joshin Yamamoto. These are Kyoto images. 1980s saw a big seminal change. We got the Carr-Parinello method came out, where density functional theory of electronic structure was coupled to molecular dynamics. Fabulous, insightful piece of work. Some interesting examples, including water and ice, were attempted, but the density functional theory at that time, the electronic structure methods, were not that good for hydrogen bonded systems, which water is, and so they were interesting, but they were far from definitive. And so we needed progress in density functional theory. This happened in the 1990s, and during the 1990s, I was, again, coming to Japan quite often. I was on several advisory boards at ICE and NIMS and so on. It enabled me to rekindle my connections with potters in Japan, and in particular followed Yuichi Ikai and have many of his pieces in my house at home. Also visited Shigaraki and all the other beautiful sites. During the 1990s, as I said, significant developments from Parinello Group, Roberto Carr, and John Perdue. But also the methodology of molecular dynamics evolved. I had brilliant postdocs in my group, Doug Tobias, Mark Tuckerman, that have gone on to their own significant careers. And you can Google them and find out. But the most important thing from the point of view of ab initio molecular dynamics was the paper of John Perdue and his collaborators, Kieran Burke and Matthias Ernzhoff, just called generalized gradient approximation made simple. This has about 175,000 citations. This must be one of the great papers in the history of science. Brings us up to the present time. Those of us that do the kinds of things that I do gathered in Messina, Italy, where Michele Parinello, who was born in Sicily, was honored with an honorary degree from the University of Messina, and pretty much everybody in that niche part of science was there, including Walter Cohn, unfortunately not in this photograph. Later in the 2000s, Michele published a beautiful paper bringing the idea of neural networks to fit potential energy surfaces. This paper has become very important, but at the time, not much happened. This beautiful paper, it was silent. Density functional theory continued to evolve. The so-called scan functional, created by John Perdue and collaborators, was shown to enable density functional theory to go all the way from hydrogen-bonded systems, van der Waals systems. Not perfect, but to go the whole swath from high-temperature superconductors all the way through to liquid water. So massive achievement. We did test it in water, a bunch of us, and it's a little bit too strongly bound, a little bit overbound. The hydrogen bonds are a little bit too strong. But that's the first decent ab initio model, I would say. That brings us to 2017. But now we enter the world of artificial intelligence, machine learning. The group at Princeton, applied mathematicians and physicists, particularly Roberto Carr's collaborators, Weinan and Linfeng Zhang, developed community codes. They're available. You can use them to do DeepMD, and coupled with the ab initio code Quantum Espresso, you can do your own modeling. At the same time, in the UK, Gabor and Stephen Elliott, under Stephen Elliott's pushing, I think, Gabor and their collaborators have been highly successful in modeling semiconductor and other type materials using these similar methods. The whole field has exploded. New algorithms and other people have entered doing remarkable work. Frank Noe and Cecilia Clemente, in particular, I'm highlighting here. I did a conference, mini conference for just a few specialists in my university has a campus in Rome, so I took advantage of that to hold a meeting there on machine learning, which really showed that this is a dominant force, at least in my area of science. The showcase work that came out that same year showed us how we could, in principle, go with ab initio accuracy, at least the accuracy provided by the methodology you're using, and extend this with these machine-learned atomic potentials to millions of molecules. I don't know that it's that useful to do that many, because in a liquid or amorphous system, you need to run the computer for a very, very long time. The bigger the system, the longer it takes to model. But this was a tour de force to show you could do 100 million. Today, you could do 1 billion particles on the biggest machines. The advantage of that is you could, in principle, see dislocations move in a crystal if you were to shear it and so on. But what has all that got to do with water? Well, the same group, Weinan, Roberto Carr, and Linfeng Zhang, and students have shown, there was a physical review letter a couple of years ago now, that showed they could model the whole phase diagram of water with terrific accuracy, really. I collaborate with that group. We're supported by Department of Energy to try and extend quantitative methods to these kinds of systems. And John Perdue was involved as well. And we investigated the impact of refining the density functionals, so-called climbing Jacob's ladder, to do higher and higher accuracies. This got a cover article on the 125th birthday issue of the Journal of Physical Chemistry. We've done a lot more. This takes me 60 years of worrying about water. We've got a couple of papers on the archive, and this particular one came out, but this one is on the archive about the dielectric constant of water. It's been accepted, I think, in physical review letters. And I have another paper just submitted with my friends and collaborators in Bangalore, India, looking at the properties of water, especially the viscosity and the diffusion constant of ions in water. No time to go into it. So this is a summary of the recent works. One came out in Nature Communications, and there are two others posted on the archive. That brings me to the end. Just gave you this historical overview of my interest in water. But I want to end with a shout for Shuichi Noze, He died in 2005, but next year will mark the 40th anniversary of his two seminal papers, and I think it would be appropriate for people in Japan to recognize what a phenomenal thing this was. And sadly, he died very young. So I'm going to end there. Thank you.
Now time is for questions, comments, please. Anybody? For water, I think most of the situations, classical description is enough.
Just in the interest of time, I removed the slides I have on path integral Monte Carlo. In the late 1970s, it became fashionable to try and implement Feynman-Gibbs methodologies. It took us into the 1980s before we made progress, and worried about how we sampled the polymer necklace beads. And, I did some work in that area, and so did others. The Monte Carlo sampling seems to be the most efficient. You do give up the time correlations when you move into path integral. Although you can do it with MD, you can't do the time correlation. There are methods out there. They're not time adequate, like I said. But yes, we can do that. It just costs a bit more time, not a lot. Essentially, you replicate your system a dozen times, so you do a bit more work. In principle, you could do it. But, and we have papers on it.
But for
It's not done routine.
For quantum system, still very fast computers cannot, I think, reproduce.
You think we should use quantum computers? Is that what you're saying?
No, not quantum computers, but the quantum, system of
yes.
it's not.
The whole, I've written papers on it, so have others. We can do that. But just in the interest of time, I did it. The protons, of course, they tunnel. So not only did they tunnel, but they also diffuse. I mean, the disproportionation of water, that we also studied. And particularly Farinello group has done a lot of work in that area. It's extremely important. I didn't have time.
Okay. Any other questions? Yes.
I'm wondering, so you mentioned that in 1950 something, you saw the first movie of molecular dynamics. So I'm wondering, so nowadays we have many softwares to make movies, but at that time, so what kind of movie and how people made the movie?
It was the same sort of movie that you would see in the movie theaters at that time. It came with a projector screen and showed a movie of particle channeling, and if you hit the right impact and huge velocity, you would channel through. It was discovered experimentally in the lab that if you had a crystal, which was being used as a monochromator for neutron diffraction and so on, but if it had the right orientation and the energy, they used a Van de Graaff accelerator, high energy ions. You would channel right through certain orientations. And then, of course, he was head of the nuclear lab there, nuclear reactors, and they were interested in radiation damage. So that was the drive.
So how accurate?
Morse potentials, very primitive Morse potentials, but yeah, so this was August of 1963.
Okay, thank you.
Any other questions? Yes, Sashi.
Thank you for your nice talk. You mentioned that the Professor Nose invented the Nose-Hoover thermostat when Professor Nose was in your group. And probably you are the first person that the Professor Nose explained the Nose-Hoover thermostat. So at that time, what did you feel when Professor Nose invented the Nose-Hoover thermostat?
Well, I would have encouraged him to stay in Canada and have an academic career there. But one day he came into my office, a few doors down the corridor from where he was working, and he said, Professor Kubo is on the phone. He's offered me a job. So I said to him, do you want to go back to Japan?
Oh.
He said, yes. Take it. It's very interesting to me. Being very Japanese, he came to get my permission.
I see.
Very special. Highly creative.
Yes.
Highly
Yes. That's true.
very sad.
Yes. Thank you very much.
One more short question, if anyone has. Yes, sorry.
I'm Shinji Tsuneyuki from the University of Tokyo, and thank you very much for a very interesting history of the research on the molecular simulation and also the study of the water. So, and also I'd like to thank that you remind us that next year is the 40-year anniversary of the Professor Nose's very important work in this field.
Papers were submitted in November.
Ah, really?
So he's 40 next month.
Okay, thank you very much. And my question, I have two questions. So first one is that because you talked very fast, so I couldn't catch up. That what is the remaining important problem on water using simulation? Another one is that I'd like to know your opinion on the quantum effect on the proton in water. What is important?
Yeah, so we do have the tools to, I mean, these ab initio potentials are, we do ab initio MD without fitting to machine learning. We're constrained by system size. Still you see the disproportion. Fortunately, water spontaneously. In fact, what we do often is to take a proton, pull it off, and measure the potential of mean force, and we calculate the pK of any molecule. This is all doable. A bit painful for thermodynamic integration, but it can be done as a consumer. So it turns out astonishing to me that these machine-learned fitted potentials are rich enough to allow the water molecule to disproportion. Case in point, for example, many, many years ago, at the Fizerev letter, where we asked, what is the structure of water in the giant ice planets on the solar system? And we know roughly the pressure temperature conditions in the core of these ice planets. And I published a paper showing that the water molecule is totally dissociated. It's a lattice of O2 minus ions with protons whizzing through like electrons. That was published 30 years after my paper. People in the lab confirmed the prediction. So these machine-learned potentials are rich enough to reproduce that phase. So it's astonishing. I mean, other examples completely different in my lab at the moment. They're interested in polymers, polyethylene, and if you tie a knot in a polymer, you break it, or if you take just a chain and break it, you make radicals, which are very reactive. They turn around and you make chemistry. They bite here, proton jumps over here, you make a methyl group here, you have a double bond here. When you pull a knot and break it, where does it break? It makes a radical. All this stuff, I mean, that was a paper I published in Nature 20 years ago without an issue. But the machine-learned potentials can reproduce this. It's astonishing. We don't care how many parameters there are. But it is rich enough. If your data set is rich enough. It's a miracle.
Thank you very much.
Okay, I think we have to close. Let's thank Michael again.